All right. I can see people are still coming, but maybe we can start, Elias, if you do not mind.
Sure.
Um, I'm very honored to have an Elias over here. Elias Fallon is an engineering group director at Cadence Design Systems. We all know about this company, I guess, and he has been involved in EDA for more than 20 years, starting from the founding of a new linear, which was acquired by Cadence back to 2004. And he was a co-primary investigator on the Majestic project funded by DARPA. The project was to investigate the application of machine learning to EDA for package PCB and also analog IC. Elias also leads an innovation incubation team within the custom IC R&D group, as well as other traditional EDA product teams. Beyond his work developing electronic design automation tools, he also has led software quality improvement initiative within Cadence, partnering with the Carnegie Mellon Software Engineering Institute. And of course, an Elias graduate from CMU. And right now he's living in Pittsburgh with his family. All right, Elias, and totally yours.
Great. Thank you very much, Helen. And thanks everybody for attending this virtual MLCAD and this talk. This is a great conference. I didn't get to attend it last year, but I heard a lot about it from a lot of people who attended, and I'm really honored to get to speak to it and attend it this year. As we were just talking about, it's great that we all get to attend so many more conferences this year because they're all virtual, but it's also harder to focus on them. So anyway, I'm excited to share my views on a lot of these trends of machine learning and EDA. As Helen said, I've had a lot of interesting opportunities over the last couple of years to do sort of machine learning research and development in more of a commercial setting than an academic setting, which is an interesting thing, and see a lot of these trends. And so I'm hoping to share some of what's going on at Cadence with you, what I see going on in a broader sense, and hopefully where we will all drive this going forward. So click in the right place so the slide moves. So, let me just start with why at least I think a lot of us are in the EDA space, is it's such a great problem space. There's so many NP hard problems. There's so many problems that are almost impossible to solve optimally, and certainly not easily. And so, we have things like Boolean satisfiability problems and SAT solvers that, go back 40 years. And we have things where we have to use more heuristic estimates, like whether it's placement or other kinds of optimization problems that the traveling salesman problem is often a good proxy for, where we have to do some kind of iterative optimization kinds of things in order to find reasonably good solutions, because finding the optimal solution will always take too long. And these are all good, hard, challenging problems. And we in EDA are constantly working on how do we apply all these tools in our toolkit, right? Whether it's some kind of iterative optimization, genetic algorithms, simulated annealing, or it's more deterministic or more analytical kinds of approaches. There's these giant toolbox of incredibly complicated algorithms that we all get to use to solve these problems. And I think that machine learning is one that is, because our problems are so hard, because there are not these optimal answers, you can't just go look up it's not just to go look up a value from a database and show it to the user in a nice way, right? There are these really intractable problems that we have to solve. I think machine learning is going to be a key tool in our toolbox going forward. And so I'm going to talk a little bit more about how that is. First, I want to talk a little bit about the context of where we're in and what we're working on. We all, as EDA engineers, we get to try and solve all these NP hard problems in the context of an ever-evolving electronic industry, right? It's something I always try and sell new hires on when we're bringing them into the EDA industry, and lots of times they've never heard of the EDA industry, is our innovation challenges never sit still, right? Because Moore's law, because the system design companies, the semiconductor companies are always designing, are always pushing the limits, doing the next thing. And right now we have all these trends going on, right? From self-driving cars, all the 5G and edge computing that is happening and coming up, the massive continual growth in data centers and cloud computing. Certainly in these work from home days of the past 8 months, we have all taken advantage of the distributed and cloud computing infrastructure that's been built over these last years. It's really hard to imagine what all of this would have been like even 10 years ago without everything that's happened. And so that's really fun. It's really cool. And it's constantly a challenge. And so, seeing how machine learning, deep learning, data science is going to continue to impact all these industries, we have to keep optimizing the systems in the silicon. And in the process of that, we of course have Moore's law. And, at this point, people have been predicting the end of Moore's law for a decade. My favorite keynote joke that I don't even,
more clear.
That I don't even necessarily, that I can't remember who I heard it from first is, the number of people predicting the end of Moore's law is doubling every 18 months these days. But the reality is it's not ending. We keep pushing to the new nodes. It's just, it gets more and more expensive. And so it makes more and more sense to proliferate how we design these systems. And it's not always about the new node. It's about different technologies, often different ways of solving the same problem, whether that's using photonics or more RF or MEMS, sensors, things like that, or other technologies, and more of a mix of technologies and things like chiplets or complex packaging and stuff like that. And so in a lot of ways, that ends up pushing the problem up, right? It's not always about just how much functionality can we pack onto a system on a chip anymore. It's about how do I design my whole system and find the best combination of things. So that sounds just like an optimization problem, right? Or at least a system trade-off problem, which is what we do in EDA, right? That's the exciting, fun stuff. But now it's even more complicated because it's outside the boundaries of just one chip and one technology. And we end up with, we've made the design space even larger, more variables, more things that can change. So in all that context, we have all the fun of AI and machine learning, and this incredible landscape of startups and new companies and existing companies building custom silicon to accelerate, to enable, to drive the AI and machine learning kind of stuff. And a couple of years ago, this was like, wow, look at all the venture capital money going into these companies and which one of them are going to get there. And now it's like, wow, look at all the chips that are out there. And again, in the EDA space, this is great, right? More people designing more new chips that are in different architectures, different ways we love it. It's great, right? More designs is more people using EDA software. It's also more challenges for us because we want to try and, again, make all of those people more productive in their designs, more successful, make those first tape outs work. And where I think we see, everyone sees things going next, and we see lots of research in lots of places and lots of companies working on this kind of whole environment, is the idea that all this machine learning and all this, deep learning and AI kinds of things are going to have to move from something that runs on big, expensive, hot, powerful servers in the data center to the edge of the network, because we don't want to transmit all that data back up, either for privacy or bandwidth kinds of reasons. So the AI is going to have to move to the edge. And again, that's a driver for more new chips, more new architectures, really innovative ways in thinking about how to represent the data and do machine learning at the edge. And again, my talk here is about how machine learning applies to EDA, and this is more the reverse, right? How EDA is having to enable all these new machine learning chips, architectures, system design, and I think it's just like everything else has been in EDA for a long time. It's a virtuous circle, right? We're enabling more and more new technologies, new chips. That enables us to do new things in EDA tools and products. That allows new chips to be built. So it's exciting stuff. I see the IoT and all the edge sensors as another area that we're going to see a tremendous number of new designs, new chips, new architectures, new systems coming in years. And our challenge in EDA is how do we continue to make that productive, continue to make that useful and interesting. And so the same kind of thing, you know, and what I want to start switching back to now is, you know, we have all the different levels of the problem, you know, whether it's how do I design the chip itself, how do I design it, how do I implement it, how do I verify it, how do I package it and put it on a board together, and then how do I put systems together with lots of those packages and boards. And there are so many of these computational software tools, and computational software is just the term we're using to kind of distinguish those kinds of tools that we use in EDA that are trying to solve these really complex NP-hard problems, or solving incredibly huge matrices and being able to simulate very complex physical effects relatively accurately, you know, purely in software, from, I don't know, regular software, right? Database lookups, web pages, things like that, right? And we have all these really examples of computational software, things like finite element analysis and meshing and SAT solvers, like I said, or iterative optimization, graph level equations, all that kind of stuff that we all have to deal with day in, day out, that are really fun algorithms. They're really interesting things. They're hard to make work. They're hard to get useful results out of, but they let us do things we couldn't do otherwise. And I think that's kind of the idea that we at Cadence are focusing on more and more, is how do we do a better job? You know, so many of these, you know, and I think Andrew said it on Monday, right? We have all these algorithms. Sorry, yeah, Monday, Tuesday, first day of the conference. I'll lose track of our days these days. You know, we have all these algorithms, and they've all sort of grown up in their own spaces, in their own technologies. And how do we better apply those tools across domains? How do we better use them and find new ways to adopt them across new problems, both either within the design of the chip, the design of the system, the design of the package, and then how the whole system goes together, analyzing the system, even within the context of all this embedded machine learning, either in the application or in how we do it. So that's a lot of the context that I see us all working in within the EDA industry. Of course, we're constantly working on kind of our fundamental core EDA tools, you know, that we think of as, at this point, these incredibly complex systems, you know, themselves. Whether you look at any company in the EDA industry, Cadence, Synopsys, Mentor, and we've got these flows of tools, each of which have many, many of these really complicated, complex optimization, computational software embedded in them, and they all have to work together in order to produce these chips. And you know, you layer in the fact that we see our customers doing more and more system design, needing to make trade-offs between what do I put on which different chips? How do I include the packaging and the PCB in my analysis of the whole system? How do I understand the thermal effect of the chip on the overall system? And then we're wanting to put machine learning into everything, both in our applications and in our use. And that's kind of the context that I find us EDA software engineers living within. And it's a really exciting time. It's always an exciting time in EDA. It's a lot of fun. But you know, from my perspective as a bit of a machine learning advocate within Cadence, I have to go convince all these teams who have, you know, 10,000 things to do this week and you know, new needs from customers that, you know, here's a new tool. It maybe uses a different language. It maybe uses some different techniques, but it's something you want to think about trying to adopt. And that's kind of the, you know, we're all very used to this problem of either, adoption, however you want to call it, crossing the chasm or the adoption curve or whatever, that, you have new technology, you bring it in, you get a few early adopters who are like, yeah, that sounds really cool, let's try and use it. And then how do you spread it to the masses? And that applies to the EDA tools that we sell and support, or IPs or systems, or anything we do in the technology industry. Machine learning is just like that. Machine learning in EDA is just like that, right? And so let's take a look a little bit at how that adoption is happening, where I see it working, where I see it having challenges, and what I think is coming up next. So just to make sure we all have a common picture, I think we do. One way we can think about these things is, I just talked about how, sometimes there's a different language, and sometimes we have to make this match between how machine learning thinks about something, or how some other algorithm represents a problem or treats something. We have lots of algorithms that work on graphs, and we all sort of intuitively, because people before us have done it, make the connection that, yeah, a net list looks like a graph, a schematic looks like a graph, and so then I can apply graph algorithms to those kinds of problems. Well, there's a whole translation process in there to go from an input to the representation that an algorithm can work on, how to control that algorithm, and then how to take the output of that algorithm, whether it's finding the shortest path through the graph or whatever, to then turn that into an output that says, and here's your route now, or some other approach like that. And so one way we talk about it a lot within Cadence is, there's kind of these two rough approaches to machine learning. We think about them as machine learning inside and machine learning outside. The easiest way to distinguish is machine learning outside is when the customer, the user, can see the machine learning happening, can see that there's some machine learning going on there, and ML inside is when they can't see, right? We're using those same kinds of techniques, but we've managed to hide it underneath, except maybe for marketing purposes. It all depends. And so, a lot of these flows end up being really, really complicated, right? We're all very used to that idea and that problem that, I make these nice boxes and say there's an algorithm with an EDA tool, but the reality is, again, if you're in the digital design flow, and you're running synthesis and place and route and iterating through that, you're using almost a completely different language than someone going through a PCB layout design flow, or an analog design flow, or a verification flow. And even getting the teams to be able to talk to each other and say, oh, you might have some data that I could use to improve the process of what I'm doing is, we can't even talk about it. We don't even have the same language. And so we spend a lot of time in EDA trying to reduce those barriers, make these kinds of go from algorithm hyperparameters to options that a user might understand. Hopefully, often we can avoid even exposing those options, but lots of times we can't. And so those are, some of the areas I think we have some opportunity to try and make things a little better. So let's get into some concrete examples of what I'm talking about and some of the research that we've done. And so this is an example of a design flow. And we all know when the arrows just go in one direction, it doesn't actually work that way. There's going to be lots of iterations. This is the design flow, the overall automation flow we put together for the Majestic analog project that we worked on. As Helen said, we just participated in the first phase, so our part's done as far as the DARPA funding goes, and we're taking a lot of the work that we did on this project now and working on how do we productize it, how do we take it into production, how do we go from that research kind of context to more of a production kind of approach. The steps in orange are all ones that we did some level of trial and had some level of success of incorporating machine learning, either in more of an inside approach or more of an outside approach, in terms of either kind of setting options, learning from past examples and data, or just kind of building more of a machine learning approach into the guts of the algorithm. So I'm going to focus on one of the early stages, this structure and grouping, because in the analog IC design flow, this is still, we talk about this being a fully automated flow, but no one uses a fully automated flow today, right? Unlike more of a digital design flow, this is still at most customers, most places, a very manual process. Or even if they're using some steps with automation and assisted, it's still a very human in the loop kind of a process. So I want to look at one of, a very simple sub problem here. And I've talked about this at some other conferences, but I think it's a really interesting example because it kind of gets to some of those really key challenges in applying machine learning to EDA, because the simplest subset of an analog circuit might be a pair of transistors, right? Most IC-based analog circuits are built in some way differential because there's inherent variability in the semiconductor process, and so you get that pair of schematic transistors. And so in IC layout, very often you'll do some kind of grouping. You put the things that need to be matched close to each other because then you have less variation in the semiconductor process. And there's not even good necessary, even after all these years and all this semiconductor work and EDA tools, there's not necessarily great ways to extract and simulate the effects of that grouping and interdigitation on matching, on things like yield. And so historically, analog design teams know what they do. They do what they do. They have their processes, their practices. They do layout design reviews to look at how are things working? Did you group the right things? Are they grouped in the right way? Are they interdigitated? And so there have been lots of approaches, constraint-based design, different EDA tools where the user would tell us, okay, here's how it should be grouped. And that works pretty well. But if we, instead of users having to do that work, what if we could learn that from past examples? And that's a great example of the idea of using machine learning as a tool in our toolbox here. If we can use past examples and kind of skip one of those steps, creating the input that tells an algorithm like a placer or something like that, these things need to be grouped and they need to be interdigitated in this fashion. That's creating the input automatically using a machine learning model based on trained data. That's a really exciting approach, and I think it's one that has a lot of promise, but it has one of those that we then run into the new machine learning problem, right? Of okay, how do we solve the fact that there's not an MNIST data set, or there's not an ImageNet data set showing all the different kinds of circuits and which transistors would be grouped together, right? And the reality is companies aren't consistent on that. Different people have different practices. You want to learn their practices, not everyone's, and they don't all have a library sitting on the shelf of here's 100 curated and clean designs with well-labeled data that you can extract and get hundreds of thousands of data points to train your machine learning model on. So you have to, there's a lot of these kinds of approaches of how do you do the most you can with smaller amounts of data? How do you do it in ways that are going to have to likely have models trained at the customer site without an EDA engineer or machine learning engineer in the loop? And I think those are a lot of the exciting challenges that we have. And in this case, by taking it from less of a let's look at the whole circuit and look at pairwise transistors, are they grouped? Yes or no? We can take a few designs, like 4 to 6, and turn them into hundreds, thousands sometimes of data points and get relatively good results. And so we found that, around that level, 5 to 7 transistor level analog designs, we're able to train models to reasonable accuracy for grouping. And what's exciting for me is seeing where it, I train it on a set of designs designed by Cadence engineers using, just kind of what we learned in school, a basic set of examples, and it gives us one set of predictions. And I train a model using a different customer's designs, their practices. And then I run them both on the same circuit and I get different predictions. They both make sense. They're both reasonable, but they're different. And that kind of reflects that the tool then is able to customize itself to the data that it was shown, to the user examples that it was given. And that's, to me, a lot of the power of machine learning and what it can potentially do in the future. And here we have kind of some of the results of embedding that machine learning model into a larger flow along the top where we're doing circuit sizing to try and improve the circuit performance and yield, and where we need to specify the relationship of parameters. So, you know, the diff paired devices need to have the same width, length, num fins, num fingers, M factor, whatever. The grouped current mirrors have to have the same kind of thing. Those would typically be constraints, effectively input the user has to create to the optimizer. But if I can replace that with a machine learning model, it gets easier to use, right? Same thing for grouping in placement. And we're able to see that work relatively well. Again, here, this is more of a machine learning outside approach, as the model is creating sort of this user visible input. In one flow, like the Majestic flow, we might use it fully automated, kind of create these inputs, run all the tools and get all the way to the end, but you could easily see how you could also do that more of an assisted way, where you create it in a user visible way, users could interact with it and then run the next step. But it also leads to an interesting problem, and one that I think is one of our challenges for working towards productization in the future, as well as an interesting research challenge. So, you know, we humans can look at, you know, say this is two input variables, and, you know, I ran PCA or whatever on them, and, you know, so they're just numbers. And then I get two new data points, right? And I've trained models based on this data to predict something useful. And I get two new data points. And as humans, we can probably look at those and say, yeah, the one on the left is probably our model's going to give a reasonably good answer. And the one on the right, I have no idea, because I didn't have any data in this space. But if I do some of the kind of simple analysis, I could say, you know, are the inputs within the range of data that I saw before? Well, yeah, it's all within the bounding box of the data, right? But it's not similar to the data that I saw before. And I think those are some of the challenges as we start looking at productization and start looking at taking machine learning models from research, where I can show interesting results and talk about accuracy and precision and recall or overall optimization flows and things like that, to a user interacting with these kinds of things. You know, how do I assure that the machine learning model that I may be trained on one set of data and I'm trying to apply it to a new set of data, how do I know it's still producing valid results? How do I know it's not, you know, making things up? And of course, we want them to make things up, but we want them to make things up within a range that we have confidence in. How do we monitor that the inputs are in the range expected for the machine learning model? How do we validate EDA software flows to ensure the software performs as expected and results in high quality results? And, you know, when things go wrong, how do we support the customer and debug problems when we've designed the software to customize itself to those users? You know, now there's answers to all these questions. You know, I think I'm not going to get into all of them today, but I think they're all ones that we all have to think about as we're coming up with new machine learning approaches to solving EDA problems. The reproducibility, the monitoring and checking of valid inputs are all important kinds of problems to think about. So another project that we worked on and are continuing to work on is the idea of predicting parasitics. So, you know, taking a set of schematics with, again, maybe a human created a bunch of layouts, maybe a tool flow created a bunch of layouts. And we've seen lots of research of this kind of approach, where rather than trying to learn something based on human designed, human labeled, human created examples, we're learning something about future flow steps. So if I start from a schematic and I run my place and route and extraction flow, and I can see what are the parasitic resistors, what are the parasitic capacitors on each of these nets, well, then I can train a model so that I can predict what the resistors and capacitors will be on parasitic resistance and capacitance might be on these nets. And I can use that in earlier flow stages. So if I try and optimize yield and performance on that circuit, and I can do it in the presence of my predicted parasitics, and I can generate those parasitics really easily because I have a machine learning model, that's great. That helps me a lot. I can try and improve the overall performance of the circuit. This was something else we did in the Majestic project. We were able to improve the estimated yield and a lot of performance measures on some of these circuits using this kind of technique as well. Here, this in some ways becomes more of a machine learning inside approach, because I can, using my own tools sort of under the black box of the whole flow, generate my own data. I can even generate random schematics or random constrained schematics that look like analog schematics that I'm used to seeing, and run place and route, you know, and generate lots and lots of data. So I can build more complicated models because I can generate a lot more data. That being said, I have all the same problems in terms of needing to monitor, is it the same kind of input as I've seen before? And obviously this would be the kind of model that is, there are some very easy ways to say, no, I can't apply this model to a new circuit because it's in a new technology. The new technology, the parasitic resistors and capacitor models, is not going to work at all. Other projects and other, you know, a classic problem, like I said, that predicting future flow steps, classifying the probability of routing. And so here we look at a PCB example. So one of my partner teams, who was also working on Majestic, but in the PCB space instead of the analog space, being able to look at a placement of a PCB and say, will it route or not? You know, being able to predict, is it a routable design or not, is a great thing, a great machine learning model to build, because I can generate a lot of my own data. All I have to do is run my own flow. Sometimes I have to rerun my flow and retrain my data because I discovered, oh, it wasn't routing because of a bug in the router. Now my model's invalid. I have to go rebuild my model. And we see this, there's academic research, a fair amount in this kind of area as well. You know, it's so, in terms of RouteNet, which was a few years ago, and, you know, being able to look and estimate congestion or routability prediction of designs is an exciting area, and it makes a lot of sense because it's this, I can predict future flow steps, I can generate my own data, train a model, and then use it effectively in earlier design stages when I'm doing that optimization. I think we see a lot of that kind of a thing, that's clearly an area that it makes a lot of sense from an EDA tool perspective. I can solve problems that I often have. So those earlier flow steps are trying to solve their own NP hard problems, and they're often having to, and often inside the loop of those optimizations, there's some heuristics that humans had to come up with, right? How do I estimate routability? How do I estimate wire length while I'm trying to optimize placement of anything, right? Placement of packages of components on a board, placement of macros and standard cells in a digital design kind of process, placement of transistors in an analog process. All of them, you know, I'm having to come up with some guess as to, is this design going to be routable when I'm done? And so plugging a machine learning model in there makes a lot of sense and is a really cool thing. And you know, you see some of that being functionality that's been released by Cadence. So in the Genesis and Innovis digital full flow, machine learning models that are kind of trained using the flow and be able to kind of learn from that and use that to feed back into the meta parameters, be able to try and drive and improve the QOR, the performance of the whole design. Either predicting slack or, you know, high congestion areas, signal integrity critical areas, and be able to try and improve them. And in that case, you know, again, it's probably the user's aware we're having to do some machine learning. They had to say, yeah, go train your models and figure out how to improve, but we're kind of hiding a lot of the details of the machine learning under the covers. Similarly, there's a tool that's been released from Cadence called Jasper Gold Smart Proof. Here, and this is always the easiest to release, where we can train the models inside of Cadence R&D, and inference only happens at the customer site. We don't have to do training at the customer site, because that's, again, that whole other level of challenge. But here, you know, when you're trying to do formal proofs in a verification flow, and there are lots of different proof algorithms for a given a proof problem, and you know, an expert user, an expert either expert verification engineer or verification R&D person can probably look at a problem and say, yeah, this proof is probably going to be faster. This proof algorithm will be faster to prove it than another, prove it or disprove it than another algorithm, but those are really complicated things. And so what the team was able to see was that by doing a lot of those in-house, measuring what's the performance of each of the proof algorithms, understanding, what are the inputs, they were able to build a machine learning model to predict which proof algorithm should I run first. And that leads to an improvement in the overall performance, the runtime needed to prove more algorithms and get to faster verification. Verification space is obviously one that's great for machine learning because there's so much data being generated. So Excellium in the simulation verification space, again, being able to run randomized test suites, build machine learning models to predict which kinds of tests or which parameter controls let things improve the coverage the fastest, lets you build a model that helps do that verification faster the next time through. And so, I think those are all good examples of machine learning and EDA kinds of products that have either already been researched or even released within corporate settings. And that leads me to kind of my view on the hype trend, the hype cycle, if you want. And if you're not familiar with this is a Gartner Inc. kind of thing. This is not and the idea is that, new technology happens sort of on the left, time goes on, people get really excited about a new technology and how it's going to impact the world. And then, we all discover it's not as easy as we thought it was going to be. Again, this probably feels very familiar to lots of us. And eventually, and sometimes the technology goes away because it really didn't work or we were just excited about it. But a lot of times for the successful ones, after we kind of get through that, oh, it's not as easy as we thought it was going to be, we figure out all these challenges to productization, not just research, and things start getting really productive. So disclaimer, there's no survey or science behind these ratings. This is my opinion on where the kinds of machine learning trends are and where they are in this whole cycle in terms of for applying them to EDA. And so things like regression models or advanced statistical models or sample-based models, there are tools that are out there that have been out there for a long time in EDA, right? They probably don't even talk about the fact that they're machine learning because it was 10 years ago, machine learning wasn't nearly as cool as it is today. And, so we use advanced statistical techniques. Well, if anybody came out with a product that used the exact same statistical techniques today, they would be talking about how it's machine learning, deep learning, AI, and everything else. But, so there's lots of stuff out there that falls in that category that is successful. I think like we just looked at this idea of supervised learning where the EDA flow itself can generate the data, train a model and use it in earlier flow steps or in the next iteration of the same flow step I just did in order to optimize runtime, in order to improve the quality of results that we see. This is something that we're seeing products be released with these days. It's clearly something that works. We've figured out a lot of the issues and we're seeing products released. So it's getting up on that curve where it's being pretty successful. I think this supervised learning on human generated data is a big challenge. I think there's a lot of potential benefit for it, but it's a lot harder because that human generated data is so much more variable that there's often a lot less of it. So you got to figure out all the techniques of how do you augment it? How do you understand it? How do you make the models train at the customer site? Things like that. I think it's going to end up coming up this curve, but I think there's a fair amount more work to happen. Reinforcement learning is obviously a huge buzzword. Bayesian optimization kind of is in there as well. I see it in a ton of papers. I see it in a ton of people are like, oh, if we just did this, it would solve all the problems because machine learning would magically make my optimization better because it would figure things out for me. And so that's why I put it kind of at the top of the hype cycle. I agree. I think there's a lot of benefit in there, a lot of potential future benefit in there. I think there's going to be, we're all going to discover all the ways it's not as easy as we hope it will be. And have to figure a lot out to make it more and more applicable to EDA. And then something that I think is still kind of coming up is, unsupervised learning. I think that there's so much data in EDA, in chip design flows, in system and silicon design flows, and there's a lot of it that's really hard to understand, really hard to extract patterns from. I think a lot of the unsupervised learning techniques, and especially unsupervised learning when I managed to stick a deep neural network in there, is something that has a lot of future potential, and we're going to see people get really excited about in the future, and then we're going to have to figure out how to really make it work. But I think there's a lot of exciting areas here, and so trying to find those ways to do research in machine learning and EDA and impact the EDA flows without access to the commercial EDA tools is obviously a big research challenge. Every university professor I talk to talks about that, and and so you see lots of ways we work around that. As I think has been mentioned earlier in the week as well, there's a SI2 working group looking at that. There's multiple open source initiatives around EDA software, and I think finding solutions to that is something we are all going to have to get better at, find answers to. Doing reinforcement learning on these enormous design spaces, when we've helped with some reinforcement learning kinds of things, I think that's one of those struggles, is how very, we all are used to reading all these papers about using reinforcement learning to, build a tool that can do Go better than humans, build chess better than humans, play Atari 2600 games better than humans. And those seem like enormous design spaces, but they're not that big compared to, the design spaces that our chip designers work in. And so I think there's a whole nother set of really interesting research problems and challenges there. The autonomous training of complex models in complex flows, when there's not a machine learning engineer sitting there making sure the model trained right and kind of poking around at the training statistics and things like that, is something that we're going to have to get good at, because to really embed these things, in the larger machine learning, deep learning industry, so many of these tools that you see that have been productized in a cloud software as a service kind of a system, where there can be somebody watching the models, more or less, and there's lots of flows for them to watch them, have software that watch the models. But I think within EDA and design, the access to data and the access, how people are going to want to work is significantly different enough that this kind of autonomous training is a really interesting problem. And as we talked about before, the monitoring, testing, and active learning are interesting areas. The reinforcement learning on the traveling salesman problem is an interesting example, because you see there's multiple GitHub repos, papers, reinforcement learning approaches, but it's difficult to use a pure reinforcement learning, machine learning approach and have it, beat the tuned and tweaked optimization approaches that have been going on for the past decades, right? And so I think a lot of the benefit in the future is this thing of how do we best combine optimization and machine learning? And to me, this comes back to the theme of these are all tools in our toolkit. We're trying to solve incredibly hard problems. We're trying to make sure we use the best tools for each problem, and how we do that kind of thing. And I think a bunch of the papers in the session after this are going to talk about some of that. How do we leverage the best of different representation, different worlds, and inject machine learning into that to try and do a better job. And so Cadence's overall intelligent system design strategy, the idea of continuing to build on all these core EDA tools that we have, build them into more and the system, the challenges and the system design problems that everyone sees coming up as we try and develop more and more complex systems, and in the presence of AI and machine learning in everything, both in terms of one of the tools we use to solve the problems, and in terms of the problems we're trying to solve. The systems that we're trying to help our customers design will have machine learning and AI embedded in them. it's just an exciting time to be working on this kind of thing. So that's where I really think that this idea that machine learning as a key part of the computational software toolbox that we all have, and as researchers, you're all helping build the specific tools, tune and tweak those tools, and figure out how they're going to apply to the different EDA problems. That's why I think this conference is a lot of fun, very exciting, really interesting to see what comes out of it, and the work that all of you have done and will do, and you know, how I think we'll see it happening and kind of being productized into the next generation of EDA tools over the next 5 years is really exciting. So thank you all for all your time and attention. I really appreciate it. I'm happy to answer any questions either now or later today, or I stuck my email on the first slide, or LinkedIn or whatever. I'd love to continue the discussion, and thanks very much.
Thanks a lot, Elias, for a very interesting presentation and sharing the capabilities and build up by Cadence. It was like just yesterday or not long ago, we're talking about machine learning for EDAs, and there have been so much things going on in such a kind of a short time period.
Yep.
I guess we are open for questions right now. There's a question actually posted on Slack, I believe. So question, Elias, to you from Vulcan Essen. Do you think generally training deep learning model in EDA area requires less amount of data compared to the googly examples?
I think that's a great question. I think it goes back to how you're applying the deep learning models. So I mean, I've seen lots of techniques used. You know, we've even seen some success using like transfer learning. So you take one of the deep vision kinds of architectures, ResNet or something like that, train it all on ImageNet, and then you just show it a few pictures of layouts if you're trying to recognize some kind of layout structure. And you wouldn't think that would help at all, but I think it's the idea that there's the really deep, learning a lot across the large data set just helps it recognize like, oh, colors and gradients and things like that. And then you can kind of specialize. And so I think there are techniques you can use like that. If you're going to limit the amount you ask the deep neural network to do to a smaller range of things, then I think you can have a smaller data set and successfully train it. But if you are asking it to, and I think that's the idea behind a lot of these kinds of approaches where we're training on our own future flow. So if I'm just training a model on this design with just a few different inputs that I'm going to change and randomly vary, and then I run my flow and I'm trying to predict, you know, which nets are going to have the worst congestion or the worst signal integrity or something like that, even if I'm using a deep neural network, I can still train a model pretty successfully to predict within that flow. I couldn't take that model then and use it on a different chip or use it at a different technology. I would have to retrain again from scratch. And I think those kinds of approaches can be successfully used with less data, but you have to be careful about it.
Okay, yeah. I actually agree with this. And Vulcan is it okay? Yeah, all right. So there's actually another question on the Zoom chat windows, and from Asma, he asked about on the productization trend. Where do you think we are at right now as an industry?
I mean, I think we're on that upward curve. I think you're going to see a lot of products come out in the next few years that talk about machine learning in EDA tools. I think a lot of them are sort of going to feel like what I talked about. They're going to feel like I'm training supervised machine learning models to optimize my flow based on data that's generated by the flow. I think the other kinds of, and so I think that's great. You know, I think there's going to be a lot more a lot more talk about those machine learning flows. You're going to see a lot of customers adopt. There's going to end up, which is, you know, and obviously it's EDA. Then there'll be bugs, and we'll all have to go figure out how to make it work, you know, even in the presence of across lots of different customers, which will give us a lot of skill at how do we do that productization. And then I think you'll start seeing a second wave of more diverse, more different, more innovative applications of machine learning that kind of change the flow more or use different things as their design data.
Elias, actually, I have a questions to you. I guess you mentioned briefly about the open source and hardware during your presentation. How do you understand that the relations of the open source communities and with like industry company like a Cadence? And what's the you know, target applications or you know, I'm just curious, like what is the ecosystems on this? Yeah.
I mean, that's a really interesting question. You know, so somebody like, so for a company like Cadence, and even for my design teams, you know, who mostly work, my R&D teams who mostly work on Virtuoso, we're in a big complicated ecosystem, right? Our customers use lots of tools, whether they be open source tools, whether they be our competitors' tools. They all have to work together one way or another. And, you know, sometimes that's through open standards, sometimes it's through the customer made it work. And then if we break it, we have to fix it, or somebody else breaks it, we have to fix it. And we see customers using open source tools in those kinds of ways. You know, I think in terms of open source EDA tools, customers are going to do that. There are lots of customers, you know, there are customers who want, you know, the vendor to give them a flow that just works and they don't want to worry about it. And then there are customers who are going to roll their own. And as EDA R&D, that works, you know, that's good with me. I mean, I think the larger open source question is just like every other software development company in the world. At this point, Cadence and every other EDA company relies on open source software, right? We use, you know, our primary development platform is Linux and GCC. You know, and if we're doing machine learning, it is, you know, it's TensorFlow, it's scikit-learn, it's a bunch of Python stuff that's all completely open source. And so, you know, I don't think there's any benefit for anybody in EDA in terms of trying to like build replacements for that or avoid that kind of an ecosystem. I think it's, you know, what we always try and focus on is just like, how can we make our customers most successful? What's the right balance between allowing, trying to make anything work, which usually means it'll take a lot longer, versus, you know, making certain flows work and trying to, you know, kind of focus on those and make them, help the customer make them work to make them most successful. That's kind of always our focus.
I see. Thanks a lot, Elias. In fact, there are more questions coming in, so I will just speed up. Another question from Vulcan. What's your perspective on the trust issue in prediction type of applications? Engineering usually has a skeptical bunch.
Yeah, and that's why, I mean, I am, so I'm a huge fan of the goal of the DARPA IDEA program that we were a part of. You know, and the goal was no human in the loop, you know, less than 24 hours, full synthesis of whatever, of everything. But at least in the analog IC space, that issue of trust was always the biggest one for me, right? Because it effectively didn't matter. Even if I did, you know, was able to take, and we weren't, and I don't know that anybody will be anytime soon, even if I was able to take any circuit and push a button and give you a DRC correct, manufacturable, electrically correct by every analysis I could come up with layout, it would take a long time for that to get adopted because people would want it, it wouldn't be done their way, first of all. And like I mentioned earlier, there's some parts of it that you just can't analyze. So I think there's a lot of hurdles with trust, but in a lot of ways, it doesn't really matter if it's machine learning or not. You know, it's one of those adoption challenges. Every EDA tool we come up with that we try and deploy something new, the customer spends a lot of time saying, okay, how does this match with what I've done before? You know, we have every new version of simulator that comes out, every new version of an extraction tool, every new version of a placer gets looked at in that kind of way. Prove to me that it's going to give me good answers and that the answers that I get are good. Machine learning makes it a little more complicated because the answers might be a little bit statistical. The results that you get might depend on the data that it was fed. And so in some ways, it's another area for things to go wrong. And that's why I think these kinds of productization challenges around how do I monitor the models are so important, because those are the kinds of things we're going to need in order to make the software perform reliably with machine learning models embedded, and that's what builds trust over time.
I see. But then there's an add-on questions to follow on this is from Felix Last. Do you see a challenge in uniting physicist-driven models with machine learning model estimates?
Yeah, I mean, it's one of those. Yes and no. So I mean, I think it's one of those great problems that everyone looks at and says, "Hey, I have a 3D solver, right? And it takes an hour to run, you know, and figure out all the physics, and it's accurate, right? We all know exactly how accurate it is compared to the real world. And wouldn't it be cool if I had a machine learning model that could, you know, give me the same answer, or 99% of the same answer within a couple of minutes?" And I think that kind of thing is possible. And but it comes to that kind of trust issue, which is that 1%. Which 1% is it, right? Is it a very important 1%, or is it a 1% I don't care about? And that's where, to me, it keeps coming back to that kind of productization. How is it presented to the user? How does the user experience that data and understand the results? And I think a lot of those kinds of algorithms are going to have to take approaches like something like Bayesian optimization or multi-fidelity Bayesian optimization, where the algorithm knows how to check the model against a reference and is doing it regularly. And any kind of result we're presenting to the user, we have a high confidence that it matches the golden reference they're going to compare to, because otherwise you're going to lose all the trust and they're not going to want to use the tool anymore.
Actually, I feel even for human beings and person by person, you know, the criteria could be various, right?
Yep.
More questions are coming on from Asma. In the examples we have seen so far, mostly it was in supervised classification problems. Have you encountered problems that require regression machine learning models?
Yes, you know, for example, the example I showed about trying to predict parasitics are regression models. We're trying to predict absolute values of capacitances and resistances, or predict timing delay, stuff like that. They're not super different. Super different from the classification problems. I think that you have to be a lot more careful about the data. It's really easy to sort of monitor the distribution of your data in a classification problem, because you can make sure I have balanced classes, or I can do things like oversampling to make sure that the classes are well represented. But when it's a regression model, I think one of the most important things is to be able to look at the distribution of training data in terms of the regression values you're trying to predict and say, is that distribution representative of the real world? Am I training on data that looks like what I think I'll really eventually see? Because otherwise you're gonna get hit with something that you really didn't expect, and it's not going to work in interesting ways.
Well, Professor Andrew Kang asked a question as well. He said, "I apologize that this is obviously tough to respond to, but that's we want our customers to be successful. So we will allow our customers to collaborate to build machine learning models of our tool and, for instance, in reference flows. Currently, the answer is no to my understanding. More than this, and my point is that there's potentially a community of well-meaning folks who would like to help Cadence customer to be more successful if they could.
Yes, and it's a great point, and it's always the challenge in terms of commercial EDA flows and the challenge of being a researcher and a developer in a corporate setting, right? You know, Cadence is motivated to make money. Most of the time, that aligns perfectly with our customers being successful. Sometimes it involves, but like I said, I think there are these challenges of unintentionally shooting ourselves in the foot. You know, unintentionally, and giving our customers, you know, so I think I agree with Andrew in general. I think a lot of times we're better off trying to make data available to our customers. I think it's about trying to make data available in the right ways. And like every other company, we have to protect our IP, our customers' IP, and that doesn't always completely jibe with providing it all in the most open and most easy to access format. And I think that's one of those challenges that we all are regularly dealing with. I agree with him in spirit. It is one of those challenges, and as always, I'm speaking for myself and my team and how we work. Can't speak for all of Cadence all the time.
Thanks a lot, Elias. I guess we are running out of time already. But you know, thank you very much for sharing very nice view about the opportunities and challenges and your own understanding as well. I hope you enjoy the platform and continue being with us and next year and the following years.
Me too. Thanks very much, everybody.
Thank you. Will you be able to stay with us and for a little longer? And I guess, and there just hopefully more questions or kind of people like to.
Yeah, I'll try and be online. I think at least all day today, and I'll definitely get on the Slack and try and answer some questions there as well.
All right, thank you.
Thanks, everybody.